Bonsoir. Nous allons suivre donc les cours d'Eric Lauga, 4 cours de suite. Avant qu'il commence, je voudrais vous présenter Eric. Il est professeur à l'université de Cambridge, au département qui s'appelle DAMT, de mathématiques appliquées et de physique théorique. Et c'est un spécialiste de la mécanique des fluides, un peu sous tous les aspects de la mécanique des fluides. Alors son parcours, il est ancien élève de l'école polytechnique, membre du corps des mines, un peu ce qu'on fait de mieux dans l'enseignement français. Et puis après l'école polytechnique, il est parti faire une thèse à l'université Harvard aux États-Unis avec 2 personnes qui pour moi sont vraiment des très grands pontes de la mécanique des fluides, qui sont Howard Stone et Michael Brenner. Et le titre de la thèse, alors je l'ai lu hier soir et je l'ai noté parce qu'il me paraît très bien résumé en fait ton histoire scientifique après. Ça commence par Slip, Swim, Mix, Pack. Puis après c'est plus long. Fluid Mechanics at the Micron Scale, a treatment of slip and mixing relevant to micron scale geometries, swimming of organisms and self-assembly of colloidal particles. Et ça résume un peu tout ce qu'a fait Eric après en développant beaucoup ces sujets qui étaient un peu à leur début au moment où toi tu faisais ta thèse et qui se sont beaucoup développés depuis sur le plan expérimental. Alors je ne vais pas vous décrire tout ce qu'il a fait. Il a travaillé donc à partir de sa thèse sur le glissement de fluides sur des surfaces solides. Il a beaucoup travaillé sur les bactéries. Alors évidemment la vision que j'en ai, elle est un peu biaisée par mes intérêts personnels, par les articles d'Eric que j'ai lus. J'ai souvenir d'un article où tu cherchais l'optimisation du mouvement du moteur des bactéries et quelles étaient les conditions maximales qu'on pouvait utiliser pour les bactéries qui m'avaient beaucoup plu. Il a écrit un article de revue qui aussi pour moi est un article très marquant dont le titre est « Hydrodynamics of Swimming Microorganisms » qu'il a écrit avec Tom Powers. Alors, il y a un truc dans cet article qui m'a beaucoup marqué, c'est qu'il y a un calcul sur la rotation des hélices de E. coli. Ce calcul, je l'avais fait et je l'ai raconté dans mon cours de biophysique pendant des années. Et c'est exactement le même, et vous faites même les mêmes approximations que moi, que le pitch de l'hélice est très grand devant le rayon parce que les choses se simplifient. Donc pour moi, c'est un exemple superbe de comment un mouvement rotatoire peut créer une force. Alors ça, c'est que le début de l'article. C'est un article qui est absolument magnifique. Il a travaillé sur les fluides viscoélastiques, il a travaillé sur la matière active, notamment avec Denis Barthelot, j'ai souvenir d'articles assez innovants de ce côté-là. Et puis, il a écrit 2 livres. Les 2 livres, c'est un premier livre qui est un peu le livre que j'ai reçu, d'ailleurs, de Cambridge University Press. Ce livre m'a attiré, je l'ai lu, et quand j'ai eu fini le livre, je me suis dit, tiens, il faut que je l'invite à faire un cours. Donc, c'est à la suite de la lecture de ce cours. C'est absolument magnifique si vous aimez la mécanique des fluides. Il y a 2 choses qui maîtrisent, je ne sais pas si tu vas en parler. Une, c'est Slender Body Theory, et l'autre, c'est ce qui s'appelle le théorème réciproque, qui est une astuce absolument monstrueuse pour chanter des calculs en mécanique des fluides. Et avec ces 2 choses-là, il fait des calculs qui, si on les prenait a priori bêtement à partir de l'équation de Stokes, c'est absolument horrible, et qu'il arrive à en faire en 5 lignes. Je vous recommande vraiment beaucoup ce livre qui, moi, m'a beaucoup marché. Donc voilà un peu les recherches qu'il a faites. Il a été professeur à l'université d'abord au MIT pendant 2 ans, ensuite à l'université de San Diego, et après à l'université de Cambridge, où il est full professeur depuis 2017. Donc il va nous faire 4 cours dont le titre c'est, alors ça dépend un peu des versions, Hydrodynamic of Cell Motion, dehors il y a marqué Cellular Motion, soit motion, soit locomotion, c'est pareil, ça va être l'hydrodynamique associée au mouvement cellulaire, à la nage si vous voulez, mais à la nage à l'échelle macroscopique. Voilà, alors c'est pas tout à fait fini, parce que j'ai un cadeau pour toi du Collège de France. Le Collège de France offre à tous les professeurs invités une médaille du Collège de France, donc je te remets, si j'arrive à l'ouvrir.
It's my first ever medal.
Sans la mettre par terre, la médaille du Collège de France. Voilà.
Ah. Merci beaucoup. Merci beaucoup.
Il faut que tu fasses attention dans l'avion, que ça ne soit pas considéré comme une arme. C'est arrivé à un de nos visiteurs.
Ah, je veux dire pour jeter sur...
Voilà. Donc à toi.
Donc là, je passe en anglais, on est d'accord?
Oui, donc il va donner son cours en anglais.
Je suis français, mais je vais faire le cours en anglais, donc ça va être very awkward. Et aussi, ça va être en Fringlish. English with a little bit of French sprinkled on top of it. So thank you very much for the invitation. It's a tremendous honor. Now it can only go downhill because, you can not ever top this. So I will try my best. So my plan is to talk about four different topics. Hopefully finish one maybe today, maybe finish it, the first topic on Wednesday. And so the emphasis will be on hydrodynamic aspects. So I know many of you are working in physics, theoretical physics, and biophysics from a perhaps experimental side or from a theoretical physics point of view. I'm not a theoretical physicist. I was trained as an applied mathematician, as a fluid mechanics / continuum mechanics person. So these are kind of the tools I'm going to be using to describe some of the things I will be talking about. So in part one, which is going to be today, and maybe the end of this will be on Wednesday, is some fundamental aspects from the fluid dynamics and hydrodynamics point of view when applied to cellular motion. So I do a little bit of biological background. I'm not a biologist, so what I will talk about are the things I've learned from reading or talking to biologists. And if you are a biologist, then you have to correct me, because some of the things, well, we'll see how incorrect this is. Then I'll talk about fluid mechanics aspects, fundamental fluid mechanics aspect, and then a specific question of flagellar propulsion. How is it that if you use a flagellum, one of those very long, slender filaments, and you kind of wiggle it around, why is it that it pushes you from the fluid? So I'm going to use slides for the beginning, and then there are some calculations or some scaling arguments that we'll do on the board, so I will kind of do back and forth between the two. So the biological background, this is a very simple schematic representation of the tree of life, with the origin of cellular life about 4 billion years, common ancestor, and splitting between what we now are prokaryotes, mostly bacteria, so I will talk a lot about bacteria 2 weeks from now, and then eukaryotic cells, and some of those we will discuss cellular locomotion aspects within eukaryotes. So eukaryotes, cells with a nucleus, prokaryotes, much simpler organisms without a nucleus. My drawings are made by my dad. My dad is a biologist. He's now retired. He likes to paint and draw, so I asked him for my book to do all of those he did himself. I did also the cover, by the way, the cover picture he did. So Jay is not my child, it's the other way, it's my dad, okay? Right, so fluid dynamics and biology, within kind of all this tree of life, fluid dynamics turns out to flows, not just fluids, but flows, the action of a fluid moving around and the stresses associated with this, turn out to be relevant to everything basically in life, from very small scales and cells all the way to the highest organisms. And generally it involves the interactions between, well, a fluid obviously, and some active type motion. And there are some things that you may have encountered, kind of papers that have had some impact. So the impact of wind on plants, flows kind of generated by swimming bacteria. These are insects that are moving on surfaces of water and create vortices. This is a very zoom in on the microcirculation in your brain, showing the very high density very tiny blood vessels, insects and birds that are flapping around and flying. Another classical hydrodynamics problem. Turns out this is a fluid mechanics problem. It's a thin film, non-Newtonian fluid mechanics problem, and without this fluid mechanics problem, the snail is not able to move. And there are two types of, broadly speaking, two types of problems where fluid mechanics is important in biology. There are flows that are inside some type of living system. For example, obviously, the blood circulation is the classical example. This is a liquid. We have airflow inside your lungs and gas exchange between the blood and, well, the air that you breathe in. We have flows inside cells on much more smaller length scales. We have things such as cytoplasmic streaming, where you have flows that are generated at the length scale. This is our plant cells. They're very large plant cells, kind of coherent flows that are generated at the scale of single cells, organized by some machinery inside the cell. Other types of problems are the opposite, which instead of happening inside something, they are happening outside. And this is what I'm going to talk about in my lectures. So we have flows around plants, obviously, and the stresses, how the stresses that the airflow exerts on the plant kind of impacts the growth of the plant. We have flows around cells. These are experiments with vesicles and shear flows. These are computations showing what happens to red blood cells and platelets. The little blue things are platelets. Kind of try to understand where the platelets are. It's important for wound healing, for example, and understanding anemia. And the quintessential outside external problem is locomotion. So locomotion from large length scales, from very large birds to very large fish swimming down to the very smallest length scale of cells, single cells or spermatozoa in this case. And so this is the world that I will be focusing on, understanding the fluid mechanics aspect, the mechanical aspects of the flows around the organism, not thinking too much about what's going on outside, but taking the problem of trying to understand what is the relationship between the geometry and the shape change of the organism and its locomotion in the fluid. So those microorganisms turn out to represent the bulk of the world biomass, mostly prokaryotes, bacteria, about 10 to the 30 cells in the universe. And their motility in fluids is a property, it turns out, of many cells and many different types of cells, both prokaryotes and eukaryotes, both single cells and also much larger multicellular organisms. And so what's interesting is that even though from a biological standpoint things are very different, they've evolved on different branches, the physics, a lot of the physics is the same physics. And so it's interesting from a mechanics or physics point of view that there's basically one way to think about it that explains everything. So there's a variety of swimming cells, and I'm going to spend time talking about two broad categories. It turns out that even though their physics are similar, the way they're actuated biologically are different. So I have bacteria that rely on appendages which they take the shape of helices. You can see a lot of wiggly periodic things. These are helices. And I have eukaryotic cells. Eukaryotic cells come in different shapes and flavors. I have cells with one of those appendages. It's called the flagellum. I have cells with two. This is a famous model organism. It's called Chlamydomonas. It's a green algae. I have cells with many ciliates, and I'll talk about those different things. So this is a sketch where I've tried, not perfect, but I've tried to draw model organisms that the community has worked on. They're basically four to scale, to relative scale. Of course, obviously, they're not to scale because the cilium is not this size. I meant relative scale. So if this is a bacterium, usually in a book, they're written with the same apparent scale, but it doesn't communicate how smaller or bigger one is relative to the other. It hopefully communicates to you that the bacterium is very, very small. It's just a few microns in length. This is, roughly speaking, 10 microns. And then I have intermediate length scale. We have a sperm cell and algae. These are a few tens of microns. And then you have ciliated organisms, which are much, much, much larger. And these could be hundreds of microns, anywhere from 70 microns to even half a millimeter, so hundreds of microns. In fact, they're so big that some of them you can see without the need for a microscope. So the question I like to ask first and to illustrate to you is how those cells actually generate the actuation that allows them to swim. So that's a biological question. And then once we understand this, we will then do some mathematical modeling to try to understand how do you quantify, how do you model this, and how you quantify this. So we start with a bacterium. So bacteria turn out to be very simple to understand. And the way they swim is they use a propeller. So the same way that if you go into a boat has a propeller, and you turn on the motor, and then the thing is rotating from your motor, and that propels the boat. So the boat is the passive bit. You're sitting on the boat doing nothing, and then the blades are rotating and pushing the boat. So it's exactly the same for a bacterium. It's on very small length scale, and instead of having blades for the motor, for the propeller is a helix. These are passive filaments called flagellar filaments, and they're chiral. They're the shape of a perfect helix. In 2 weeks, I'll talk about what those shapes are exactly, why they're helices, etc. But basically, take my word for it, these are the shape of semi-rigid helices in red, and they are rotated. They are rotated by a motor, which is embedded in the cell body. And to transmit the rotation of the motor, which is in a fixed coordinate system relative to the body, because it's moved with the body, to the flagellar filaments, which are free to move around, then there's something that transmits one to the other, which is a kind of a joint, universal joint called the hook. So this is a single polymer. This is another polymer, much more flexible. And this is a motor that rotates. So the motor rotates the hook, which rotates the filament. And if you rotate, and we'll talk about this in more detail, if you rotate a chiral shape in general in a viscous fluid, it pushes you. In general, there's a force along the axis of rotation. So this is what it looks like. Here, I have illustrated 3. It turns out when you rotate all 3 with the same rotation, they all bundle together behind the cell, and they make this kind of effective thicker helix that rotates like a bundle. It's called a bundle of helical filaments. And that rotates together kind of coherently in synchrony, and then it pushes the cell forward. And the model organism that people have used for this is E. coli. And Howard Berg, who passed away just a few months ago, he's basically the person who was at Harvard. He discovered everything about this. And I had the privilege of working with him on a project, and it was very, very inspiring. So here are movies showing you this process. So there are, see a few fluorescently stained bacteria that are swimming. Sometimes you see just one thick fluorescent bright helix behind the cell. Sometimes it looks like the helices come apart, come back together. I will explain this process in 2 weeks where we'll talk about bacteria. But hopefully, seeing those movies kind of are allowing you to get intuition of what was going on. On the right here, you have the same, but slowed down, so that's even easier to understand. And you can see that the rotation gives rise to this apparent wave, which propagates. Obviously, there's no propagation of material line points because the helices are just rotating. Every point on the helix is just moving along in a circle in the frame of the cell. But of course, if you rotate the helix, it looks like there's a wave. So you get those apparent waves propagating, and the cell is moving forward. And there's a variety of organization at the cell level of how the flagella are coming glued to the cell. Either they're coming at different points, called peritrachus. This is the E. coli. Or, so this is when you have many flagella. Some of them you have one. Some of them you have many, but they all come from the same place at the one pole of the cell instead of being kind of almost randomly distributed. Some of them have flagella which come on both sides. And so they're kind of an entire zoology that exists of where the flagella are, how many you have, and how they're organized. But the physics is basically all the same. And this is what happens now. A lot of people in physics, I'm sure you've heard from Jean-François and other people, how bacteria kind of self-organize into those very large-scale motions with coherent length scales much larger than cells themselves, and also very large fields. So they're kind of collective physics of bacteria. So this was bacteria. And eukaryotes also use something called a flagellum. So for a bacterium, I should have said, the piece together that is the motor and the hook and the flagellar filament is called a flagellum. One flagellum, multiple flagella. Here, this is also a these are also flagella. We give them the same name, but they're not quite the same. So the joke I always do is I'm saying, this is like comparing a Ferrari with a French car. Okay, the bacterium is the very basic French car. I love French cars, but it's not a Ferrari. This is much more complex, much more intricate in its design. So this is how it works. I'm sure some of you already know this. So in this case, the flagellum is basically essentially some sort of muscle, active filament. So the same way that in your muscle fibers, you have fibers which are sliding relative to one another, powered by molecular motors, which are doing mechanical work, transforming basically chemical potential energy into mechanical work. Here it's very similar. You have a structure. If you kind of cut this and look at the cross-section, it's the structure of filaments, polymeric filaments. In this case, it is not actin, but it's microtubules. So there are actually pairs of microtubules. And those microtubules want to walk relative to one another. They want to slide relative to one another. And because they're geometrical constrained, this sliding is transformed into bending. So if you combine sliding with geometry, you're going to get bending very naturally. And this is, in fact, this picture is from an experiment from Charles Brokaw. He was at Caltech at the time, who was one of the two groups, his group and another group in Hawaii, showed at the time in the 70s, demonstrated that indeed it is this sliding. And the way they've done it is they removed the membrane that is around this, and they were able to glue gold beads, one on one filament and one on another filament, different one, and they could, by measuring the distance between the gold bead as a function of the kind of the waving motion, they could actually measure the amount of sliding and relate this to geometry. This is one of the famous experiments from that time. And so this is what it looks like. By the way, that's one of the movies that Charles Brokaw used. So this is in the swimming frame. So you make it so that the cell body is always at the same place. And you have a traveling wave, a wave of deformation, which propagates. Now, clearly, again, if you take a material point on the filament, it just goes up and down. It oscillates up and down. But obviously, if you, just like a rope, if you were to do this to a rope, you would look like there's a wave of material point moving. They're not moving. It's just that the phasing of the material point gives you some optical illusion, or I don't know exactly whether it's the brain or something, but you feel like you have points that are moving. Now, the last type of cell is called a ciliate. So a ciliate is a type of eukaryote that instead of using one flagellum, like a sperm cell, or 2 or 3, uses hundreds of them. And the model organism here, I know some people work on this already, or have in the past, is Paramecium, And this is a single cell as well, but it has, as you can see, hundreds of those small cilia. In that case, it's the same actuation, it's the same internal structure with the filaments, etc., but they're short and they're stiffer. They're short, that means that effectively they're stiffer. And in that case, we just give them a different name, even though they are flagellum. They're just flagella. They're just short versions of this. And the cilia turns out to be, can also not only have them on microorganisms, but we have them in tissues all over our body, in the lungs, in our ears, in some of our organs. And in that case, instead of propelling the locomotion of a cell, what they do, they're basically pumping fluid. So you have them, every time we cough mucus out, cilia, hopefully healthy cilia, have been able to help you get rid of some of the dust particles you've trapped in your lungs. And so they're used also to transport. And in that case, the motion, instead of a waving motion that I illustrated in the previous slide, I remind you of this. This is a waving motion. In that case, if the flagellum is very small and becomes a cilium, it undergoes typically a two-stroke motion. Because the cilium is anchored near a surface, you see that the surface length scale is much larger than the cilium. So from the point of view of the single cilium, it's like it's glued to an infinite surface. And in that case, it undergoes a two-stroke motion where it extends into the fluid, pushes the fluid, and then hides from the fluid to return. So you kind of break some symmetry, and on average, you create a net force. And there's a very nice explanation in Albert's book, the free version, which is on the NIH website. I highly recommend you look. So, extends. This is called the effective stroke. You push against the fluid, as much drag as possible. You entrain as much fluid as possible. And then to the return, you're basically hiding from the fluid. You're hiding because you're next to a surface. The surface is no slip. The fluid is not allowed to move. So therefore, if you move next to that surface, you're going to basically transport very little amount of fluid. So a little bit, obviously, because of the fluid is moving with you, but it's very limited to where the cilium is relative to moving the other way, where you, in that case, the length scale, which is typically the height above the surface where you are, is much larger, and therefore the volume is going to be much larger. And there are interesting questions that come with cilia, and that is that instead of having one flagellum, if I only have one flagellum and I describe to you how the flagellum deforms, that's all you need to know. But if you have many, and they all deform the same way, you have additional degrees of freedom of the coordination. Are they all moving in synchrony, or do I phase them and do I get waves? So these are called Methachano waves. They are waves, and there are two types of waves. There are waves where the effective stroke of the flagellum, the cilium, so where it basically pushes at every stroke the maximum amount of fluid, is in the same direction as the coordination wave. This is one type of waves. But there are some that go the other way. So paramecium, for example, is one where the effective stroke is in the direction opposite to the wave. And there have been a lot of studies trying to understand, from a purely biophysics and biofluid dynamics point of view, what is the advantage of doing one versus the other? Can we understand this? So this was my few-minute introduction to the biological aspect. As I said, I'm not a biologist. I hope I haven't said too many stupid things. This is what I understand from talking to the community and collaborating with a lot of biologists. Yes?
I ask a brief question. You only show cases where the heating was pushing the object. There are cases where it pulls the object. And in my mind, but I'm not sure it's true, it's associated with the boundary condition at the link between the object and the cilium. Do you have any comments?
So Jean-François' question is, I show examples where I have a wave going one way and the cell goes the other way. That's what you're saying. The wave could go the other way. So there are some cases in biology where the wave goes the other way. And because this is typically, this boundary condition here is typically kind of one of similar to, in solid mechanics, we would say clamped, is basically anchored. The cases in biology where it goes the other way have been identified as due to something else. And the something else is the microstructure of this flagellum. So if you have a flagellum that have hair, their hair has specific names in biology called mastigonyms, those hair change the kind of the relative friction coefficients of your flagellum. And if you have hair that are sufficiently dense or sufficiently long, then actually the flagellum, instead of pushing you, and you end up being kind of dragging yourself through the fluid. So you reverse.
The one that go backwards have small hairs?
Correct. Small, but sufficiently long, or small and sufficiently dense. So there's a kind of criterion. This is also work from the 80s, late 70s and 80s that I've figured that out. It's a very interesting thing, obviously. Right. In particular, it's used, I should say, just to finish your question, it's used for feeding. So if I'm an organism, and I'm not a swimming organism, but I'm basically using flagella to create flows, there are cases where it's better there's two ways to create flows for you. Either you push fluid away, and then you get recirculation from the side, or you go the other way. But the problem is that some organisms have a structure which would not allow the recirculating fluid to come in. It's like a rigid, like dog collars that some dogs have after. Well, so in that case, what you need to do, you don't want to do that. You want to go the other way. You want to bring the fluid down to you directly within your. In that case, you need to change the microstructure to bring the fluid down. So you need to reverse the relationship between the wave and the fluid. So this is an example where that happens in organisms in the ocean. I hope this answered the question. Okay, so fluid dynamics aspect. So now we're going to switch to fluid dynamics. Some equations, a little bit of using the blackboard. It's late in the day, I know. I will try to do as much or as little as is possible. So here, imagine I have an organism. This is my paramecium. It's embedded in a fluid. So the fluid will have two characteristics. The density, you all know what this is. Turns out a normal fluid has also another thing, which is the viscosity, which is something about the friction, how much force you need to slide. If you take two amounts of fluid between two plates, if you slide this, there's a force you need to apply to this, and that's proportional to the viscosity. So water has a small viscosity, honey has a much higher viscosity. And my organism in this fluid, it has a typical size L, and it moves at a typical swim speed U. There are two timescales which are going to govern the dynamics of the fluid around. One is an advective timescale. So that's the timescale it takes in the frame, if I'm sitting with the swimmer and I'm moving, that's the timescale it takes for any perturbation to the fluid to be advected downstream from me. So if I create a perturbation in front of me, then it's going to go down about my length scale on a time of about L over U. Now there's another timescale which has to do with viscosity. So viscosity is known to lead to basically diffusion of perturbations. So this is a diffusion problem, essentially. For example, if you were to inject some rotation in the fluid, local, what we call vorticity, some local swirling in the fluid, it will dissipate away, kind of go away like a diffusion problem, exactly like a diffusion problem. So in that case, it's a diffusive timescale, and that diffusion coefficient is the ratio between the viscosity and the density. In that case, that ratio is called the kinematic viscosity, and it has units of a diffusion constant. So L square, so rho L square over mu is another timescale. So if I have one timescale and another, I could just divide one by the other, and I get a number that's dimensionless. That's the famous Reynolds number, just applied to the locomotion case. So Reynolds, for those of you who have not studied turbulence and or fluid dynamics, then you should study fluid dynamics and or turbulence. But if you haven't, this is a one-slide summary of what you need to remember. Is Osborne Reynolds was an engineer at university that is now called University of Manchester, and he has a very famous problem, a paper that he sent to the Royal Society in 1883, where he reports on the discovery of something interesting, that if you look at flow in a pipe, if you increase some combinations of the parameters, for example, the mean flow in the pipe, or the viscosity of the fluid, then, or the size of the pipe, then you can get a transition, a sharp, dramatic transition between a very simple laminar flow. So this is an example of an experiment showing this. Boring flow, just totally along the pipe, nothing happens, to something weird, where suddenly the flow creates a lot of eddies, totally chaotic, and not very, can really predict what's going on. And this is called turbulence. This is historically the first paper kind of understood in the community as the paper. And that person is Reynolds. And in his paper, he says, well, it's weird. It looks like it's the combination of those numbers that give me exactly a transition that actually governs the transition. And those combination is a dimensionless number. And now we call that number the Reynolds number. So it's the same Reynolds number. So if you apply this to the issue of locomotion, so here are some organisms which are kind of ranked by length scale from bacterium all the way to very large organisms, here a sperm whale. Then the Reynolds number, if I take typical length scale, velocity, and frequency, the Reynolds number increases. So I have the smallest one is 10 to the minus 4 for bacteria. Just need to be careful with time. 10 to the minus 4, all the way to, for the locomotion, for the largest fish and mammals, 10 to the very large numbers. Okay, 5, 6, 7, easily, no problem. And so there's a clear kind of boundary between things where the Reynolds number is less than 1 or much less than 1 and things where the Reynolds number is above 1. And so this is what I'm going to talk about. Now what's interesting is, so far what I told you is that our description. Here are length scale, here are time scales, here are velocity scales. Let's calculate the Reynolds number. But I haven't really told you what it means to have a small Reynolds number versus a large Reynolds number. Is there a way to interpret, to go home with an intuition of what it means from a fluid mechanics standpoint? So this is what I'm going to try to do now. So here's a very simple calculation. It takes 5 minutes to do on the board. Every time you see this, it means I need to switch to the board. So imagine I have a swimmer. It's a typical swimmer of size L. It's my fluid. Density, oops, I'm missing a rho and a mu. It should say a density rho. I'm sorry about that. Viscosity mu. That's what I wrote right here. Density, viscosity. The swimmer itself has its own density. Might not be the same as the fluid. So rho s, as in swimmer. And that swimmer is moving around nicely. And suddenly the swimmer decides, you know what? I want to stop swimming whatsoever. I'm not moving. And I'm going to ask, how much am I going to be able to glide in the fluid before I stop? So you know that if you go to the swimming pool, you do this, and then you're tired, you stop. You're not going to instantaneously stop. You're also not going to go for 10 kilometers. That would be too easy. There's some length scale in the middle. So how much in distance will I go before I stop? So we can estimate this very nicely. So to find the length scale d, then I need to, of course, apply Newton's law. So it's Newton's law that's going to say how I decelerate. So I'm going to have the mass of the swimmer times the deceleration, which is due to drag force. It's the drag from the surrounding fluid which will slow down the swimmer. And the drag has a different scaling at high versus low Reynolds number. And this is why, so if I have high Reynolds number versus low Reynolds number, then I'm going to have different drags. So let's use this equation. So this equation, I'm going to approximate du dt as the typical speed by which I start. So I was swimming at speed u over some time scale tau. So I'm going to say, I will try to estimate that time scale, that basically the order of magnitude before I stop moving whatsoever. Okay, so this equation means that mu over tau is f. So that gives me an estimate for tau. Tau is mu over f. That's the typical time scale before I stop. Now, if I have that time scale, and I used to go at a typical speed u, so u is going to go from u to 0, that means that the typical length scale that I'm going to be moving, d, is on the order of u tau. There's a scaling for the length scale, which means that I'm just going to multiply this by u. So that's going to be m u squared over f. That's the typical length scale by which I'm moving. So I told you that at low and high Reynolds number have different scalings for the drag. At high Reynolds number, the drag is on the order of a typical pressure times a typical surface area of a swimmer. And the drag is a high Reynolds number drag. Unless the organism is very super nicely streamlined, then in general that pressure is going to be a Bernoulli pressure. So it's a square of a velocity times the density of the fluid. Okay, this is from high Reynolds number fluid mechanics. Okay, this is due to Mr. Daniel Bernoulli. So if you have taken any undergraduate course in fluid mechanics, then you know this basically from that name. Okay, so if I have this, that means that my force is on the order of rho u squared L squared. And therefore, if I apply this to this formula, I'm going to get that the distance d, which was m u squared over f, f is rho u squared over L squared. So that's going to be m over rho L squared. Now m I can simplify. So I can use the fact that the mass for the organism is typical the density of the organism times its volume. Okay, of course there's geometrical prefactors, but that's just shape. If we were a sphere, that would be very good. If we were elongated things, well, there's a different prefactor, but you see what I mean. So therefore, this is rho s L cubed over rho L squared, and therefore this is rho s over rho L. So that means that I found my first result, that is the ratio between d, the typical size of gliding, divided by the typical size of the swimmer, at high Reynolds number. That's simply on the order of the density ratio between the swimmer and the fluid. Okay? So that's very interesting, because that says that if I'm going to the pool, my density is about the same as the fluid, so that's 1. So basically, I'm going to glide by a length scale of me. I'm not going to glide a nanometer. My experience tells me that I can do better than that. But I'm also not going to glide the whole swimming pool, because my length scale is 1 meter or 2 meters. Okay, depending on the number of meters that your length scale is. You see my idea, right? So you know you're going to do 50 centimeters, 1 meter, and then you have to do it again. You have to swim again. Now, if you're a bird in air, then your density is orders of magnitude above the density of air. This is the density of the swimmer itself relative to the fluid. So that's, say, 10 to the 3, 1,000. So if you're a bird, you flap your wings, and you stop, you're still going to continue for thousands of times your own body length before the air stops you. Now, a bird obviously has another problem to worry about, and that's gravity. So I haven't told you about lift. There needs something else that balances the weight. But forgetting about gravity for a second, where if you're a bird, it's difficult to do, but you see my point. This is just the air stopping you. So this was at a high Reynolds number. At low Reynolds number, the force has a different scaling. The force is going to be what we call a stress times the surface area. And my viscous, this is due to viscosity, and the viscous stress is the typical viscosity times what we call the shear rate, which is basically the rate at which the fluid is being sheared, is being moved. And so that's the inverse time scale. So that's U over L. That's the relevant shear rate. So that means that your stress, your force at low Reynolds number is on the order of mu UL if you multiply this by L squared. OK, so that means that now I can calculate my D. My D was M, which was rho S L cubed, times U squared divided by F. And F, I told you, is mu UL. So that means, I'm sorry, I should have organized the board a little bit better. This means that D over L, so if I divide 1 by 1 power of L, I get well, there's a cube divided by 1, so there was 2 left. If I divide by 1, there's only 1 left. So that's with L at the top. Powers of U, I have 1. I have a rho S, and I have a mu. And that is very, very close to the Reynolds number. To within, if I was to change this density by the density of the fluid, that would be exactly the Reynolds number. So therefore, I can rewrite this as D over L at low Reynolds number is rho S over rho times the Reynolds number. Okay? The Reynolds number being rho UL over mu. So at low Reynolds number, you have a different scaling for the force. You have a different scaling for this length scale. That length scale now becomes, yes, you still have the density ratio, but now it's multiplied by the Reynolds number. Now, if you're a small organism in a fluid, that basically is the 1. So it's really the Reynolds number. So an interpretation of the Reynolds number for an organism is that dimensionless length scale, the ratio between the gliding distance to your scale, and that's essentially 0. So if you're a bacterium, for example, for bacterium, then L is on the order of 10 to the 6 meter. It's a micron. And therefore, with a Reynolds number of 10 to the minus 4, then you have D, which is on the order of 10 to the minus 10 meter, which, of course, makes no sense. Within the continuum limit, this is 0. This is exactly 0. So this is an instantaneous world. If I go to the pool and I swim, I can take a breath for a few minutes or for a few seconds, and I'm going to continue to move. If I'm an organism, I don't have time to basically breathe at all, because if I stop moving, I stop instantaneously my fluid. It's an instantaneous world. So that's the kind of the intuition. This is an instantaneous world. This is the intuition I wanted to convey about the Reynolds number. All right, so as a result, if I'm a small organism, my world is a world of viscous fluid dynamics, not that at a high Reynolds number fluid mechanics. So what are the equations I have to solve, and what is it that I'm faced with every time I want to solve a problem where I would like to model how a cell is moving in a fluid? So I have my organism. This is some shape at time t, and this is some shape at some other time, t prime above t. I would like to figure out how that organism moves in the fluid. OK, so what do I have to solve? So I have to find the velocity field, u, and the pressure, p. My fluid is what we call a Newtonian fluid. So if it's a Newtonian fluid, that means that I know exactly the relationship. These are simple fluids, not viscoelastic, not polymer. A Newtonian fluid is a fluid where I know exactly what the stress state is in the fluid, and I can relate the stress to the pressure and the flow. So the stress in that case is a tensor, is the pressure, the isotropic part of the stress, plus a viscosity times things about the gradients of the viscosity. of the velocity. Okay, every time I have a velocity gradient, whether it's a shear, whether it's a rotation, whether it's an extension. Oops, I think I broke in a million little pieces this pistol choke. Then every time I have this a velocity gradient, I'm generating a stress, and obviously I also have other types of stresses, which are pressure. Now the equation of mechanical equilibrium, there's no inertia, and so therefore my stress always has to balance at every time, and that's the divergence of the stress is 0. So that's mechanical equilibrium for a fluid that has, for a continuum material that has no inertia. Okay, this is due to Koshy. This is called the equation, Cauchy equation of motion for any continuum material. Now, because I know sigma, I can plug in the stress, and I get the equation, which are the famous Stokes equations. Stokes equations for a fluid at low Reynolds number, and that is that the gradient of the pressure has to balance the viscous stresses. So this is the equation I'm trying to solve every time I'm solving for a fluid flow outside, in a simple fluid, Newtonian fluid, outside an organism. Now I should add that my velocity u cannot be arbitrary. My velocity u is incompressible, because with those velocity scale, I'm not able to exert stresses so large on the fluid that I will compress it. So it's an incompressible flow, which means that in addition, I have another equation, which is a constraint, which is that divergence of u is 0. Okay? So if you've never dealt with the Stokes equation of solved fluid mechanics problem, this looks weird because it's kind of one equation with two unknowns. But remember that there's a constraint. This pressure, in some sense, in a mathematical sense, in fact, you can show mathematically that you can write down the Stokes equation as a solution to a variational problem. And the Lagrange multiplier in your variational problem is P. It exactly is such that is the Lagrange multiplier for the divergence. So if you're kind of minimizing a Lagrangian where you're allowing the velocity field to not be divergence-free, you bring it back to be divergence-free using a Lagrange multiplier. It's exactly this grad P. Okay, so nice kind of calculation, classical calculation. Okay, so these are the equations I'm trying to solve. Now, the important thing for swimming is what are the boundary conditions that I have to put in? What is it that I know about boundary condition? What is it that I don't know? So the boundary condition for this equation, so boundary conditions, is that u on the surface of the swimmer, so I'm going to call S my swimmer, u on the surface of the swimmer is a mix. It's a mix of swimming, which basically I'm trying to solve for, plus deformation, where of course the deformation is imposed. Okay, so when you go to the pool and what you're doing is you're doing this. This is the deformation you impose. You don't say to the pool how fast you should go. It's basically your aerodynamics and how bad of a swimmer you are or good of a swimmer. So the boundary condition of your body is therefore a mix of things you know and things you don't know. So the simplest way to write this is to basically, it's a sum, obviously. This is what it looks like. So the boundary condition is going to be, a part of the boundary condition is going to be what we call the gate. This is what we call the swimming gate. This is you moving your arm and imposing in a moving frame how the body deforms. Okay, this is deforming the body in a prescribed way in the moving frame. So if I'm sitting with the swimmer and I'm observing the swimmer, this is how the swimmer deforms its body. Plus things that I don't know. I have translation and I have rotation. Okay, so I hope you can see in blue because I broke the yellow. Usually yellow is the best. So now I'm worried about the blue. Can you see the blue on the board? No, the answer is no, not great. I'm sorry, there's no more yellow. There's only crumbles now left of the yellow. So the U is translation. So basically my cell has instantaneously some amount of translation in 3 directions. So this is 3 degrees of freedom. And there's, of course, rotation. So my cell could also instantaneously rotate as a rigid body in 3 axes. So it has 3 degrees of freedom in translation, 3 degrees of freedom in rotation. So that's 6 degrees of freedom that I have to solve for. It's not obvious. This is an example. This is one example. So there are other cases. I was about to say literally this. So there are other cases. So you can have this case right here is called what we call imposed kinematics. So this is in the case where whatever stresses are internally generated are so strong that they are able to control the shape that they're moving. But we know that's not kind of perhaps the way some organisms move. For example, if you go to swim in water, in the swimming pool, you'll do one way. If I throw you in a pool of honey, it will be very hard to do exactly the same way. Why? Because the stresses from the honey are going to feed back on you in however way you're generating forces. So there are other ways. You could have fixed or imposed stresses. In some cases, you can have energetics. So basically, it's neither kinematics, not stresses, but how those two together combine. For example, the rate at which energy is expanded locally near the organisms, and any combination of those. So this is an example of boundary condition. Now, in this case, in the fixed kinematics, I have 3 degrees of freedom to find, 3 degrees of freedom in translation and rotation, so I need 6 equations. So I need 6 equations. And those come from the fact that the organism is free. So the organism is free. So that means that at any time, the force due to the fluid, F from the fluid on the organism as a vector is 0. That's 3 equations. And the torque, or the moment, however way you decouple, however you want to define it, is also 0. And those together gives me 6 equations. Okay? And in a fluid, the force is defined as the integral over the surface of the surface traction, which is the dot product between the contraction between the stress and the normal. So if I call n the unit normal sticking out outside my cell towards the fluid, that's the force, and the torque is simply the moment of this, x cross sigma dot n ds. So in some sense, swimming is kind of like an eigenvalue problem, where I have to find the magic values of u and omega. There are 6 numbers that I just adjust exactly so that at every instant, f is 0, t is 0 for all time, forever. And I do this in a quasi-steady fashion. There's no inertia, so time is basically a parameter. You just jump through versions of time, and that's true for all times, okay? That's true at any time, okay? So whatever the time you're looking at, f is 0, t is 0, and therefore you find u and you find omega. Right, so let's see how I'm doing with time. Okay, it's already almost, okay, late. So I had another slide here. I'm not going to do the derivation where I wanted to talk about energetics. You can show mathematically that the rate at which the surface is doing work in a fluid, so if you call, I'm not going to do the derivation, I'm just going to show you the result. So if you call the rate at which the swimmer is doing work against the fluid, so this is a power. This is the surface integral of the local instantaneous boundary condition, u, which I wrote right here, u, dotted with the stress. And if n is the normal sticking out, then you need a minus sign to make sure that this is positive. The swimmer is doing work constantly to swim. You can show through some classical mathematical derivation, okay, so this is homework. You open your favorite Stokes flow textbook and you do this work. Turns out that is 2 mu times, well, this is mu times the integral over the volume of the fluid all around the swimmer of a number that is positive, dui. This is basically, I'll say, it's grad u plus grad u transpose double contracted with itself. Grad u plus grad u transpose, and that's a half dv. Okay, so that number is always positive. So the swimmer is always doing work against the fluid, and that is basically the rate at which energy, mechanical energy, is lost to the fluid through dissipation. This is rate of dissipation of mechanical energy. Rate of dissipation of mechanical energy. And that's due to viscosity. Okay, so my swimmer keeps imposing a boundary condition. That, by the way, that's true for whatever boundary condition I'm imposing, whether it's fixed kinematics, fixed stress, you name it. That result is always true. That is the work done by the swimmer. At every instant, all the work that the swimmer is doing it's sent instantaneously all the way into the entire fluid to be dissipated away. All that energy is lost, that mechanical energy is lost, and is gone into the fluid as internal energy. All right, so some important consequences of living in a Stokes flow. One consequence is that there are two important things, and I hope that I'll have time to cover both today. One important result is that the distance traveled by a swimmer is independent on the rate at which it moves. So if I give you a swimmer, so I had prepared a whole proof, but in the interest of time, I'm just going to sketch what I mean by this. This is property number one. Property number one is what I call rate independence. So imagine I have a swimmer, and that swimmer starts at t equals 0, and ends up at t equals t final. Okay, and it goes with a sequence of shapes. So I'm going to label this is shape t equals 0, and then I have a sequence of shapes. I keep breaking chalk, I'm very sorry about this. And this is shape at t equals t final. Okay, so if you go into the pool, this is the beginning shape, and then you're doing whatever you want, and then this is the final shape. Now, I can either go through this at one rate, so I'm doing actually, let's say it's linear rate, but I could also go through this at different rate, where I'm going slowly and fast, so I have shapes which are, two shapes go very quickly, and then I slow down between two, and I do it again. It turns out, because the flow that you have is a Stokes flow, you can show mathematically, very rigorously, as rigorous as you want, that it's independent of the path you take. All that matters is that you've taken pictures of all those shapes, and that you know all the intermediate shapes. Now, whether you play this movie of pictures going fast and slow down, it doesn't matter. Mathematically, you can show that it doesn't matter. All that matters is the sequence of shapes. Okay, so the rate information is totally irrelevant in a Stokes flow. Another important consequence is that of reversibility. If I have a fluid, which is a Stokes flow, this is a famous movie from G.I. Taylor. G.I. Taylor, in this movie, injected, I should pose. Oops, I don't know if I can pose. So this is a very simple illustration. OK, fine. So what he's doing is he's injecting one fluid into another. It's just that, well, it's the same fluid, but one has a dye in it, so you'll see it red. And he's going to mix the two together. And then he's not cheating. He's just going to unmix them. He's mixing them by just going backwards to the sequence of deformation that is done. OK? So you'll see there's no cheating because you can see these fingers. So OK, you go. Dye, red dye into the fluid, same viscous fluid. This movie is on YouTube. You can find it. And, he has an hour-long movie. OK? And remove the needle. And then look at the finger where the finger is going. Go on one side, and then you push, you rotate. Right? So the drop of fluid now has been clearly mixed. It's almost disappearing. You can see a little bit of trace of red, but it's lost forever, never to be found again. And then the finger is going to change its position. So the finger was on this side. So see, finger goes now the other way. So this is not the same movie playing backwards. Time still goes forward. It's just the finger is now doing something different. And then this is what happens now. The fluid is a very viscous fluid. Okay, I believe it's a silicone oil. So that's orders of magnitude more viscous than water. And the fluid that you start with goes back exactly where you started. Okay? And the only difference is a tiny bit of smearing from diffusion. Of course, obviously, this thing diffuses, but because it's very viscous, it diffuses very slowly. So you see, you apply deformation, you do all sorts of crazy things, and then if you undo it, you completely undo all the deformation, and you end up with where you started. So this is a fact that happens at very low Reynolds number. Do not try to do this at home with a tea bag. It's not going to work. If you put your tea bag and you rotate 3 times, and then try to undo it by rotating 3 bags the other way, you will never be able to undo this, because it's a very high Reynolds number, whereas this is completely, so if you could do this, do tea in a cup of silicone oil, then yes, it will work. But do not drink that, because that's, OK. So that's silicone oil. So very low Reynolds number, kinematic reversibility. And the consequence of this, the consequence of kinematic reversibility with this rate independence property is something called the scallop theorem. So the scallop theorem says that if you have a sequence of shape now, so here I told you all that matters is the sequence of shape. So I don't need to think about the rate. All I need to do, I can erase this, all I need to do is to think about my sequence of shapes. So I can therefore just look at the sequence of shapes. Here are a bunch of pictures that I took. And then I can say, well, will this collection of pictures lead to locomotion, yes or not? Well, what the scallop theorem says is that if the sequence of shape of a swimmer is identical, so it moves this in a periodic fashion, if it's identical when viewed under a time reversal transformation, then you cannot swim. So what this means is the following. Just schematically, if I can take 2 minutes, what this means is I start with a shape at t equals 0. And I finish with a shape at t equals t final. Now, if those shapes going one way are the same as the shape going the other way, then that means that this shape is the same as that shape, right? Because clearly, otherwise I'll be able to make a difference, yes? So same with the next one. The next one, there is a immediately next one to this one going backwards, which is the same. So I can do this mapping, and there's a mapping, so this one goes to this one, and then there is a point in the middle, which I can therefore identify when I converge, which is the middle. Yes? Is that clear? So clearly, my sequence is 2 bits. There is first half. I can mathematically define this as the first half, and this one as the second half. And what we've learned from the rate independence is that, well, kinematic reversibility says that the second half going forward should be exactly minus the opposite of the second half played backwards because of reversibility. If I do one thing one way, and if I do something the other way, then it's the opposite, yes? So if I call this A, and I call this B, then I can generate minus B by going this way is going to be minus B, yes? So B, let's say A is this way, let's say B is this way, therefore now I have minus B going from right to left. However, minus B is the same sequence of shapes as A, because, well, I start with the same, and then the next one is the same, and then the next one is the same all the way to the end. Yes? And so therefore, those two are exactly the same, and they completely cancel out. And therefore, I get 0. So the amount of locomotion is 0. So therefore, in order to be able to have a swimmer, you need to have, and I'll stop in a minute, 1 minute, promised, not more. In order to have a swimmer, you need to beat this. This is a constraint. You have to live under this constraint and find a way around this constraint. So there are multiple ways to do it. One way to do it is to not have rate independence or reversibility. So that happens when the fluid is not a simple fluid. When it's a nonlinear viscoelastic fluid, then the rate at which you do things matter. Take a viscoelastic fluid and shear it slowly or shear it fast, then the response will be very different. Then you can have 1 degree of freedom things that move. One other way to do it is to not have 1 degree of freedom. So, consequence of this is that if you have only 1 degree of freedom, those things like something opening in 1 degree of freedom or 2 spheres around, then those 2 things will exactly average to 0. These are, the motion is always going to be some sort of exact derivative of deformation, and you cannot move. So you need to bypass this if you're in a simple fluid. So, well, 1 degree of freedom doesn't move, so you need at least 2 degrees of freedom. So here are examples of 2 degrees of freedom. Purcell, Edward Purcell, in a famous paper, proposed this as the simplest swimmer that works. So it's kind of like a very simple schematic wave where you have a swimmer with 2 arms, and then it goes up, up, and down, down. In some sense, it's the beginning of a wave, and that's enough to swim. It has been studied. It has been put in the lab. You can have the same thing with spheres, much simpler to do in the lab. In fact, people have used optical tweezers to make this. It's called a 3-sphere swimmer, and they've shown that if you have 3 spheres, they use 3 lasers, and if you have 3 spheres and you move them with a nice relative phase, then in fact you can create a pump. It's either a swimmer, or if they're fixed on average in position, then it's a pump. And of course, if you have now continuous degree of freedom, what is the deformation? If you think about it, what is the simplest way to have a deformation or a sequence of shapes that if you play one way, they will be obviously different than if you play the other way? Well, the answer is a wave. Because if I have a wave that propagates in one direction, and if I play the movie backwards, then it will propagate in the other direction. So clearly a wave indicates a direction of time, and this is how organisms do it. So organisms are allowed to bypass this constraint, not by using complex fluids, they're in whatever fluid they are, but by actually undergoing deformation, which are not. The sequence of shape is not identical to time reversal symmetry. If you take pictures of swimming bacteria or take picture of the spermatozoa and the shapes that it shows you when it swims, well, and you play that sequence of shapes backwards, then it's not identical because you had a wave. So a wave went one way, and now the wave goes the other way. And this is how they bypass it. Okay? So that's what I wanted to say about kind of some of the fluid mechanics and some of the mathematical constraint. I didn't have time to do kind of this proof as formally as I wanted, but you have it in books. It's freely available. It's been proven even by people in pure math, kind of as formal as you want, whatever is your flavor of math that you like. You also have scaling arguments in the spirit of what I did today. And I hope that will be enough to get the intuition. And next time, I'm going to talk about eukaryotes. And to understand swimming eukaryotes, we have to understand flagella and how flagella are able to generate propulsion. So that's what I'll do, and I'll then do sperm cells on Wednesday also. Thank you very much.